All right, we'll get started. So I wasn't able to print out my notes, so I'm going to try and read them off my phone. It'll be a little annoying, but it should work. Okay, so there was a question about the midterm. What's going to be on it? I'm not sure, never had a midterm because I've never taught this course. Definitely, I just want to try and make sure that everyone's sort of caught up and is understanding things. So there will be some questions just basically trying to probe that you understand what's going on. And then maybe a couple that might stretch you a bit and not necessarily looking for all the class to be able to answer them, but just to identify people who are really into this and really getting it. But it will be, if I can make it multiple choice, I will. It's easier for me to mark, but I don't know with this, it might be hard to like kind of reduce all the questions down to multiple choice, but I'll try and see. But it will be basically just testing the concepts and the theories, sort of like that, yeah. Trying to gauge whether you understand what's going on. So to study, like just concentrate on like, do I understand it? Not, can I repeat it? Anything that you can repeat, you can put on your cheat sheet anyway, so there won't be anything that's just like a straight repetition of some fact. It would be more whether you understand what's going on. So if I show you, say, the same thing in a slightly different scenario, you would be able to know what it is and how to deal with it, roughly. Yeah. Sorry, I couldn't hear that well. Something about math questions.
Yeah, we have math questions. Also going to be as an MCQ.
Yeah, so that's what I'm saying. If I could put it into multiple choice, I would, even if it was a math. So then you would have different answers as your options, but it might be easier to just have you write out stuff. We'll see. Yeah. Okay. Other questions about that or anything else? So I wanted to give you an assignment before the midterm, but the midterm's coming up quickly. So I think I'll maybe give you the assignment before the midterm, but then make it due after. So it's our midterm reading week, and then maybe the week after I'll have it due. The first assignment will be more like a general assignment of trying to looking at use cases of zero knowledge, just so that you can sort of see the big picture. It's not going to be a technical assignment or anything like that. It'll be more just writing about a particular use case, but I'll try and post it by next week. Okay, other questions? No. Okay, so last class we talked about commitment functions. And where we left off, we had just started talking about something called the Peterson commitment. So that's where we'll pick up. And I'm going to grab a copy of the two tables because we'll use them. Okay, so Peterson commitments continued. And as a reminder, this is the multiplication table and the exponentiation table. This is modular multiplication, and P equals 23, Q equals 11, and this is modular exponentiation, and P equals 23, Q equals 11. Okay, so Peterson commitment, what we do is we commit to a message. It's randomized, so we're also going to take a second number, which will act as a sort of random number, scrambler. We're going to produce a commitment. And the way we're going to do it is we're going to do G to the message, just like the Feldman commitment that we saw, but we're going to add an extra term. We're going to add an H to the R, and H is just some other generator, some value from GQ. And then everything else is as we described before, this is from GQ, this is from ZQ, this is from ZQ, and the output of the commitment will be from GQ. Then if we want to reveal the commitment, we send the commitment, we send the message, and we send the randomness. Okay, so you can't open it or reveal it unless if you remember the randomness, so keep that in mind. And it's going to return either a true, false, and it's basically just going to say whether G to the M, H to the R equals this. I mentioned before, I'm going to start not writing mod P, but because everything is mod P, okay? We're never going to see anything anymore that isn't mod P, or if it's not for whatever reason, then I will make it explicit, but you can just assume that this is always there. Okay, so let's do an example, and then we'll talk about whether it's sound or hiding. Sorry, whether it's binding or hiding. Okay, so what's a message that I might want to commit to? So it can be anything in ZQ. Okay, so any of these numbers I can commit to. Just pick your favorite and shout it out. Someone said 6, great. No one said 6. Okay, the randomness, we are going to select at random. Okay, so like it's not your arbitrary choice. So let's say I throw a 10-sided die, 11-sided die, and the answer is, say, 3. Then I get 3. All right. I need 2 generators, and these will be public parameters. Okay, so this is my choice. And these are public parameters. Public parameters means that someone else chose them. So just like they chose that you're working mod 23 and all that stuff, they'll give you a G. And then H we can set to 13. These have to be in GQ, remember? So we can't, they can't be any integer, they just have, but they can be any integer that's in GQ itself. Okay, we'll talk a little bit more about H. It's a little, you have to do something extra to deal with H, but anyways, we'll get to that in a sec. I mentioned at the start of class that the printer wasn't working in our office, so we had to, I have to fiddle with my phone to try and see my notes. Okay, so what we're going to do is we're going to compute G to the M, H to the R. So G is 2, M is 6, H is 13, R is 3. Okay, so we can use our table. So 2 to the power of 6 is 18. 13 to the power of 3, 13 to the power of 3 is 12. 18 times 12, 18 times 12 is 9. Nine is in GQ as we expect. Everything inside both of these tables is in GQ anyway, so we're never going to get something that isn't. And so that's our committed value. Okay, so I just committed to this number 6. Say we're playing rock, paper, scissors. That could be the number that we're using for rock. So now I'm locked in that particular number here. If you commit to rock, you will choose a different random number. Okay, you'll choose 4 or 8 or something with high probability. And so you'll end up with a different commitment. Okay, so if you're like, I think he committed to rock, let me commit to rock and see what I get, you're going to get it probably with high probability, you're going to get a different output. And so that's why this is better than the previous commitment scheme. So we can't do that attack. Okay, so let's think about whether this is hiding or binding. Okay, so for hiding, basically I know G, I know H, I don't know R, I don't know M, and I do know C, okay? So this is what someone sees. And the question is, can I solve for M? Okay, can I figure out what M is? If I can solve for M, then it's not hiding. And if something stops me from solving for M, then I'm going to get, it will be fine. It will be hiding if I can't solve for it. Okay, so the first thing is there's a bit of complexity here because I have 2 inputs. So I have M and R as well. As a first step, let's just ignore the R part and just say that I don't know what it is, but it's kind of like fixed or something. I'm just going to kind of move it over to the other side of the equation. Okay. Then what is M? M is going to be the discrete log base G of C over H, the R. Can I compute this? I can't, right? Discrete log problem is hard. Okay, so what does that mean? It means I can't solve for M. What does that mean? It means if I see these 3 things and I don't know these 2 things, I'm not going to be able to figure out what M is because I would have to break a discrete logarithm. In order to do that, we assume that that's not possible. Okay, so it's going to be hiding based on the discrete log problem. Okay, but we did cheat a bit. We cheated a little bit with this R value. Okay, we assume that we could kind of move it over, but if we don't know what M and R is, we don't know how to split this value between G to the M and H to the R. We don't know where to pull it apart. Okay, now let's go back to the table here for a second. Oh, actually, okay. So what I'm going to do is I'm going to show you a table of every Peterson commitment, assuming that G is 2 and H is 3. Okay, so I'll make another table. Okay, so what this table is it's just like the other tables that we've been looking at. It's specific for G and H. So we can change G and H to other values, but then we're going to get a different table. Okay, so but assuming that G is 2 and H is 13, what this table shows you is the output. So the values in white are G, which is 2, raised to the power of the row, times H raised to the power of the column. Okay, so these are all the possible random values that you could use. So these are the values of R, and these are the values of M. And I hope that's right. Well, let's double check it. So we said that committing to 6 and 3 gives us 9. So if I go here and go 6 and 3, so maybe I did it right backwards. So 3 and 6 give you 9. Let's see, what was 6 was the message. Okay, sorry. So I reversed these two. So the columns are every possible message, and the rows are every possible random factor that you could use. Okay, so we can read this table. Okay, now when we did this commitment, the output was 9, right? I committed to the message 9. Okay. Imagine you have infinite powers, so you can look at this table and you're allowed to scan the whole table. Okay. And I tell you, I committed to something, I'm not telling you what it is, but the output was 9. What is the message that I committed to, looking at this table?
Not sure, because there's multiple 9s.
Okay, so everyone sees there's multiple 9s. Okay, so is it possible that if I committed to the message 6, there is a 9 with randomness 3 that gives me that value, but maybe I committed to the number 2, right? There's also a 9. It has a different randomness. It has randomness 2, but it also gives me a 9. Okay? Anything else? So there's multiple. How many 9s are in this table? There's one in every row, or every column. Yeah? So every column has a 9. Okay, so is this hiding? It's actually better than, we call this computational hiding because you'd have to break a computational problem. But in this case, even if you could break the computational problem, you can solve any discrete log. You have infinite power. You still can't figure out what message I committed to because I literally could commit to any message. Okay, so a Peterson commitment commits, when you see the output, the commitment, it could, in theory, be a commitment to any message. Okay? So we call this unconditionally hiding. So this is great for hiding, but we're going to have a big problem when it comes to binding, right? Because now I can open it up to any value. Okay, so we'll think about that in a second, but for now it's looking great. It's unconditionally hiding. So what that means is that given a commitment and the G and the H, there exists an M and an R such that C is the commitment to M and R for all M. So any M you want, there is some M and R pair that when you commit to it, it's going to come out to this specific value of C. Okay, so there'll be, if the specific value of C is 9, given G and H, then for the message 4, randomness 8 will give you 9. For message 9, randomness 1 will give you 9, et cetera, et cetera. Okay, now binding. Is this scheme binding? Binding means that I commit to rock, then I see your answer, you decommit, and you paid paper, and now I'm like, I'm about to lose. I would rather open my commitment up to scissors than I can beat you at the game. Okay? So if I commit to rock, can I open it up to scissors? So in theory, if let's say that, say 0 is rock, 1 is paper, and 2 is scissors, I lost track. And the commitment, whatever I commit to, let's say I commit to rock. So I give you the value 9, and I say this is my commitment. You don't know that it's rock. Could I open it up to paper or scissors instead? So I can. So I would have to know, what would I need to know to open it up to something different? I would have to know the other R value for that, okay? So this is not binding. If I can figure out I'll just write what I said, the other R value, but then I'll say it a little more formally. So what that means is that I commit to, I'll call it M1 and using R1. I want to change M1 to M2, okay? And so now I need R2, okay? Such that the commitment of M1, R1 comes out to the same value as the commitment to M2, R2. Okay, can I compute that other R value? Maybe, maybe not. Okay, let's see, let's try and work through the math and see if I can commit that too. Okay, so this is what I know. I know that I computed G to the M1, H to the R1. And in theory, what I want to find is, this is an unknown, but I want to find an R2 here. So I don't know what this value is. These values I do know. I chose them. Okay, and I'm choosing what I want to open it up to next. I know G. I know H. And I know the output value of the commitment. Okay, one equation, one unknown. It's solvable. Okay, the only thing that's going to stop us is if we hit something like a discrete log problem. That's the only thing that we'll see in this class. If I hit that, then it's solvable in theory with infinite computing resources, but it's not solvable in practice. Okay, so this is going to work as a commitment scheme. It doesn't work if it's not binding. So I want it to hit the discrete log problem. If it hits the discrete log problem, then that's good. Then now it's a working commitment scheme. Okay, so let's just play with this a little bit and see if we can isolate R2. So we'll try and move stuff around in the equation to get R2. So what I'll do is, I'm gonna, there's some other thing that I want to take you to, so I'm gonna not do it like the most simplest way. Actually, do you know what? I'll just do it twice. Okay. So what I can do is I can just move G to the M2 over to the other side. So now I get G to the minus M2. And I have H to the R2. Okay. And this is the same as G to the M1 minus M2. H to the R1. All right, how do I solve for R2? So I'm going to have to move R2 from the exponent down to the base. How do you move things from an exponent down? So logs, okay, so I have to take the logarithm of it. So R2 is going to equal the logarithm base H of everything here. Do I know what this number is? I do. I know G, I know H, I know M1, I chose M2, and I chose R1. So I would have to like multiply it and do the exponents or whatever, but I can get that down to a single number, okay? So this is a known number, it's just some element in GQ. So I have some number in GQ, and I want to take the discrete log of it relative to h. Okay, can I do that? I can't. Okay, I can't take arbitrary discrete logarithms. Okay. What's the question? This will be in GQ, yeah. So anytime there's a very simple pattern, which is just that exponents, let's see, where did I draw that? Here. Exponents are in ZQ and base numbers are in GQ, always, yeah. There's nothing fancy with GQ and ZQ, it's always just, if you're just talking about exponents, it's in ZQ, and the base elements are in GQ, yeah. So here, because we have base elements, it's going to be in GQ. Okay, so this looks promising. There's a but. Let's say I know something. Let's say I know, what's the relationship between G and H? Okay, so G and H are both in GQ. That's actually what I was looking for. So they're both from GQ. If I wanted to turn G into H, what would I have to do to it? Actually, I shouldn't say what would I have to do. I'd either have to multiply it by something else to get H, or I could exponentiate it with something else to get H. So they're both sufficient. Let's focus on the exponentiation case. So let's say that H is G to the, all right, alpha. First off, is this true? Is there some alpha so that G to the alpha gives you H? Okay, so we can look at our table. So G is 2 and H is 13. So starting with 2, is there some number so that 2 to that number gives you 13? And so the answer is yes, there is. Okay, 7. So 2 to the 7 gives me 13. Okay, what do we call alpha? If you look at this equation, there's a name that we've been using for what alpha is. Let's say I want to solve for alpha. How do I solve? So I do a logarithm, and alpha is a discrete logarithm. Okay, so we say alpha it's the logarithm or the discrete logarithm so it's the discrete logarithm of h base g, if you want to be specific about it. You can do it the other way around too. So there'll be another value, say beta, h to the beta equals g, but we'll just think about it in one direction. Okay, so in the future, what I'll do is I'll just say dl. So the dl is the discrete log of something. Okay, all right. Do I know what that value is? Okay, so I just said that G and H are 2 and 13. I said they're public parameters. What does that mean? It means, I don't know, NIST chose them. Does NIST know the discrete log between these two? They might, right? They can easily set it up. So they could start with G first, then raise it to the power of something 9 and say, okay, we're going to use H as 6. Meanwhile, they know that 9 is the discrete log between the two. Okay, so we don't know who knows what about the discrete log between the two, but let's think about whether you can do anything useful knowing this fact. Okay, so I'm going to go back to this exact equation. I'm just going to write it out again, but this time we're going to use the fact that maybe we know what this is. So I'm going to say C equals G to the M, H to the R, M1, HR1. And what I'm trying to do is I'm trying to find a second message. And when I commit to the second message, I have to figure out what the randomness is to go along with it. I want it to come out with the same commitment. All right. Using the fact that h is g to the alpha, what can I write here instead?
G to the alpha times R.
All right, so g to the alpha, if you want to do it first as this step, you get this. Okay. We can do the same on the second side. So g to the alpha, whoops, this should be multiplication. All right, and we can simplify this. So what happens when you do an exponent to an exponent? They multiply. And if you have the same base, so you have g to the something and you multiply it by g to something else, what happens? They add. Okay. So I'm going to get m1 plus alpha r1. And this is going to equal m2 plus alpha r2. Okay. I can get rid of the g's on both sides. So m1 plus alpha r1 equals m2 plus alpha r2. And then what I can do is I can try and solve for r2. Okay, so I'll move m1 minus m2. I'll keep the alpha r1 over here. Then I have alpha r2. And then I can divide it. Yeah.
Equals to g power alpha. Why are we assuming that?
Over alpha, right? It's not
Yes, thank you. Yeah. Okay. So let me try and re-explain this. First off, does alpha exist? Forget about whether we know it or not. There is some alpha, right? And there's only one alpha as well, okay? So now we can live in two worlds. We can live in the world where I know alpha or I don't know alpha, okay? So let's assume that I'm in the world, so let me just write this explicitly. So alpha exists. Okay? I might know alpha. If I know alpha, then I can do what I just described here. Yeah? If I don't know alpha,
But there is no alpha because we know g and s, right? So we can always calculate it.
yeah, but so that's right. So let's ask that question. I know G, I know H, I don't know alpha. It's one equation, one unknown, but why can't I solve for it? So it's a discrete log, right? So alpha equals log G of H. Yeah, so sorry, I just see discrete logs everywhere, so I assume that like everyone's just comfortable with it, but yeah. So alpha here is the discrete log between G and H. Okay, so if you know the discrete log between G and H, then you're able to compute R2. If you don't know it, then you go back to this and you hit a discrete log problem and you can't solve it. Does that make sense? Okay. Okay, and then just one quick thing here. While I have this equation, I'm just going to slightly rewrite it as m1 minus m2 over r2 minus r1. Okay, so that's just the same equation rewritten, and well, I'm going to say something about that later, but yeah.
Maybe I'm mistaking something, but H should be G to the power.
Sorry, yes, you're right. Thank you for that. That wasn't a mistake, it was my mistake, yeah. Sorry, I'm just switching the letters. Now, it doesn't matter if you know the discrete log in one direction, you can compute it in the other direction. All you do is you move it to the other side and it becomes an inverse as well, but yeah. Okay, so if I know this, all right, so let's go back to this binding question. Is a Peterson commitment binding? The answer is it depends. If you know the discrete log between G and H, it is not binding. And we can say something more. It's actually very efficient. You can open it up to any message you want and you can figure out what those messages are. It's very efficient to do. Okay? So you can lie about it. Okay? But if you don't know, it looks, I haven't proven it yet, but it looks like I'm not going to be able to break binding without solving a discrete logarithm. Okay? And that will be the answer. So that's the answer. So if I don't know the two, then it is binding. And now I want to say something even stronger. I want to say that if you can ever find two commitments that are different, that open up to the same, like two different M's and R's that open up to the same commitment, you can break the discrete logarithm between G and H. You can turn that knowledge into the knowledge of what the discrete logarithm is between G and H. What does that prove? That proves it's exactly as hard as solving the discrete logarithm. Okay? So if you, so I'll write this as a fact. Where they're not equal, just write. The trivial case is that M1 equals M2 and R1 equals R2, but we'll see. I forgot the verb. Okay, if you find two M1 and M2 pairs, where M1 and M2 are not the same, and the commitments are the same though, so the output is the same, you can solve the discrete log between G and H. Okay, so I want to show you visually that this is true, and then we'll write down the math for why it's true. Okay, take another look at this table. Just forget everything that we talked about. What can you tell me about the table itself? Does it have any structure to the table? Okay, so nines are structured.
The sequence are.
Okay, what about the sequence of integers? Does it change ever? Okay, every row has the same sequence, but what's different about each row? They're not copies of the same row. So what's different? They're shifted. Okay? So row 2 is shifted. It's the same as row 1, it's just been shifted over. Okay? By some amount. Okay? Now what about row 3? It's also a shift. Is it the same amount or is it a different amount? Same amount. Okay? So every single row is always shifted by the exact same amount. Okay? What is that amount? Yep.
When you say exact same amount, you mean like the whole number is just shifted, something like
Yeah. So what I mean is, like, let's do the 9 since they're circled. So I start at 9. I want to actually count to the left, but we'll count to the right for a second. So I go over 1, 2, 3, 4, and then I go down to 9. Yeah. Then if I do it again, 1, 2, 3, 4. Yeah. So that's what I meant by it's always the same amount. The next one is always over 4. Okay. Now if I count backwards, okay. So let's say I start with 12. And I say, okay, how far back do I have to go before I hit the next 12? So 1, 2, 3, 4, 5, 6, 7. 6, 7 is 12. Okay. And then another 7 will be 12. Okay. So the count back is 7. What's the discrete log between g and h for the g and h that we chose? I think I wrote it down. I swear I wrote it down, but anyways. But we can find it. Yeah, I agree. Yeah, so let's find it. Okay, so G is 2. And H is 13. Oh yeah, I circled it, but I didn't write it down. Okay, so what's the discrete log? 7. Okay, how far did we count backwards? Or if we shift to the left, how much is the shift? It's 7. Okay, that's not a coincidence. So if we change G and H, we'll get a different table. The shift amounts will be different, but the amount that you count back for the shift will always be 7. Okay, so in other words, if I can figure out what the shift is, then I can break the discrete log. Okay, and even if I pick 2 random numbers, like let's say that okay, I don't want to get ahead of myself. So let's just catalog what we know, and then I'll say what I was going to say before. Okay, so if you find 2 M1 and R2, you can solve the discrete log problem. And the equation that you can use is this one that we wrote here. Okay, so the discrete log alpha will equal M1 minus M2 over R2 minus R1. Okay. Now here, when I was talking about the shifts, I was talking about the row, like going to the next row. So the difference between the rows is 1. Okay. So the difference between the rows is 1. So this is just 1 on the bottom. And then M1 minus M2 is M1 shifted backwards. That's the minus to where it is in M2. Okay. So that's why, so this equation is telling you the same thing that I just showed you visually. But this equation is a little better because let's say I know there's a 12 here and the other 12 I know is like way down here, right? Now they're not side by side. I have to move over a certain number of messages, but I also have to move down a certain number of rows, okay? But as long as I know the differences between the two messages, so I know 10 minus 1, and I know the difference between the rows. So this was at row 0, and this is at row 6. Then I can plug it into this equation. I'll have a number here. I'll invert it and multiply, and then I'll be able to solve for the discrete log. Okay? Yeah.
Alpha should be large, right?
Sorry.
Alpha should be big.
So it's the same thing as it's the same parameters that we had before. So P should be more than 4096 is the current kind of thinking. And Q should be at least 256 bits.
We're making H using G. If we do it randomly, maybe it will get small, but it won't. Right?
Okay, so say your idea again, because it's a good question to ask. So what do you want to do? So you want to do something with G, make what small? Okay. So G, because G is in GQ, What that means is that you'll go through Q elements before you repeat. So there is no small g's or big g's. There's no like G or H that's like worse or harder. Because we made them all in GQ, this was actually one of the reasons why we did it, is there's no bad G's or bad H's. They all are going to have the exact same order, which is Q. Yeah. So the discrete log for any of them is going to be as hard as any other one. Okay. Let's say I want to solve a discrete log problem. Okay. What I do is and let's say it happens to be between the numbers that we're using, 2 and 13, but it could be between any arbitrary numbers. Okay. The method I showed you before is we just scan along the row until we hit 13. Then we've solved it. We figure it's in the 7th one. Okay. How much time does it take to scan across a row? Relative to the length of the row. So let's say, tell me, how long is this row in terms of a symbol? This is Q, right? So the length of this is going to be Q. So in order to scan a row of size Q, it's going to take me about Q times. Okay? On average, maybe it'll take half of that, but it's going to be order Q kind of thing. Okay? Now I have a totally different approach to solving a discrete logarithm. I want to use the fact that if I can find two commitments that come out to the same value, then I can also solve the discrete logarithm. Okay? So what I do is I take the discrete log I'm trying to solve, and so it's between two values, and I make them G and H. Okay? So this is a discrete log problem algorithm. All right, so let's say I need to find the discrete log between G, I'll call it X and Y just to make it a little different. Okay, so what I'll do is I'll set G equals to X, I'll set H equals to Y. Okay, then what I'll do is I'll just pick a random M and R, okay? And then I'll compute the commitment to it. Then what I'll do is I'll say, have I seen that value before? Okay, have I seen, this will come out to some value C, have I seen C before? Probably I haven't seen it before, so then I'll just go back and I'll repeat this step. Okay? But maybe I have seen it before. I'll just double check that maybe by accident I chose the same M and R, right? So maybe I'm getting the same C value because the M and R values are the same, right? So I'll ask if the M and R is different. So again, if it's no, I'll just go back. But if it's yes, then what I do is I just plug it into this equation and I've solved it. Okay, so visually, what does that mean? Think of this like a big dartboard. Okay, so first off, I set the discrete log I'm trying to find. I'm trying to find it between 2 and 13. So I make this table. I don't have the table because I can't create it, but conceptually I have this table. Okay, so there is this table. What I can do is I can look up any element in this table that I want. That's what I can do efficiently. Okay, so once I lock G and H, then I have a table that looks like this. Then it's like a dartboard. So I just throw a dart somewhere. It's going to land on one of these numbers. And I say, oh, that's a 13. And then I throw another dart, and it lands at 6. And then I throw another one, it goes to 8. This goes to 18, 12, 2. And every time I'm saying, hey, have I seen this number before? Okay. And then eventually, I am kind of just trying to do this random. Tell me if I hit the same number. Did I get 2 6s before? Yeah, okay. Let me back up to that point. Okay, so here I threw one, I got a second 6. Okay, are they the same? Is it because I threw it at the exact same place in the dartboard? No. Okay, they are different places in the dartboard that both happen to have a 6. Okay, then I can compute the shift. So I know that I'm going to shift a certain amount going to this row, then the same amount, then the same amount. And when I apply that shift, I'm going to end up here. Okay, and so I can figure out what that shift value is, and that shift value is the discrete log. Okay, how many darts do I have to throw before I get 2 that are the same? So this is a Q by Q dartboard. Okay, so the size of this is, there's Q rows. There's Q columns. Say, just say, I just didn't hear what you said.
Q plus 1.
Okay, so it could be something relative to Q. I don't need something that specific. So who thinks that it would be about order Q? You have to throw about Q darts to hit the same number. No one has any idea, but it's fine. Who thinks it would be more?
More.
Okay, more? Anyone think it's going to be less? Okay, some people think it's going to be less. Okay, I wouldn't be showing it to you if it's not less. Okay, so that's the other way of thinking the psychological thing. Okay, if it was more, then it's a worse algorithm than just scanning along the row, just scan along the row. Okay, turns out it's less. Okay, how many, let's say I scan along the row. Let's think about it this way. So I'm trying to find the discrete log between 2 and 13. And I don't know anything about the table, so let's just assume it's random. What's the probability that the 13 happens to be sitting here in the first one? First one's a bad example because it's always going to be 1. But let's say I go to the second one. It's going to be 1 out of Q. Okay? Then it's going to be 1 out of Q, 1 out of Q, 1 out of Q, 1 out of Q. Okay? So every one I look at, I have a 1 in Q chance of trying to find it. Okay? What happens here? What's the probability that... I really want to make this the same color. What's the probability that when I throw a dart here and I throw a dart here, that they have the same number? It's also going to be 1 over Q. Okay, so we're going to have a 1 over Q probability. Okay, so and then let's say I throw a dart here. What's the probability that these have the same? 1 over Q. Okay. All right, so if I throw 3 things, I get 2 1 out of Q probabilities, but I also get to check whether these 2 have the same. So I get an extra connection. So I can check if that's 1 over Q. Okay, then I throw another dart. It should be 1 over Q, right? But I also get to check whether this matches this matches this, right? So I get some other 1 over Q probabilities. Then I throw another dart, right? But I also get to check whether it matches this, whether it matches this, whether it matches this. Then I throw another dart, and I get to check it against, and the past darts that I'm checking against are growing. I'm checking even more options. So the more darts I throw, the more chances I have of matching. Okay? So here I get to check against all of these. Okay, so what does that mean? It means that I'm going to get a match a lot quicker than if I'm just scanning along the row. Okay, because every dart I throw, I get more and more chances. Okay. So how fast can I find it? So this probability, it's kind of weird. There's a name for it. Anyone know the name for it? There's a famous name. When I say the name, you'll be like, oh yeah, I've heard of that, maybe. Okay, so this is called the birthday paradox. Okay, and it's the subtle difference between 2 questions. I can ask everyone in the room, who has the same birthday as me? Okay? The probability that each of you have the same birthday as me is 1 over 365, roughly. Okay, and there's whatever 30 of you, so then there would be 30 chances at 1 over 3 to the 65. Okay, so we understand that probability very well. The birthday paradox is if I change the question, I just say, what's the probability that 2 of us have the same birthday? Now, normally in your mind, you're thinking, oh, it's probably around the same. It's like 1 in 300. Okay, but think of every combination. It's like I could have a birthday with any of you, but each of you could have a birthday with anyone else. And so there's a lot more possibilities for 2 people to have the same birthday. How big does a room have to get before 2 people on you would expect would have the same birthday? Doesn't have to get that big. It has to be like 30 or 40 kind of people. If you get 40 people in a room, I forget what the number is, but let's say it's 40, then there's like a 99.9% chance that 2 people are going to have the same birthday. Okay, so that probability is like a lot lower when you think about it. That's why it's called a paradox. There's nothing illogical about it. It's not what you would think as a human. So that's why it's called a paradox. But anyway, it applies here. And the complexity, so sometimes we write, oh, that just means like relative to Q, how much work do you have to do? So scanning the row, it would take about Q work. Here it's going to be the square root of Q. Okay, which you'll know is the same as Q to the half. Okay, all right. So if Q's 256 bits, right, it's 2 to the 256 bits. Because we can solve it at the square root, the effective security is actually only 2 to the 128 bits. Okay? So NIST says that we want 128-bit security, and that's why we choose Q to be twice as big as it, because you can break discrete logarithms with at least birthday paradox, so square root complexity. Okay. Now, the side note, though, is it does take OQ's Q root memory. So you also have to store all of these. So if you go home and you're like, I'm going to break some discrete log problems, you have to store a lot of integers, and then you have to compare your newest integer to everything that you've stored. Okay, and so it's not the best algorithm. There's better algorithms that have the same time complexity without this huge memory complexity, but it's an easy algorithm to understand. Okay. Okay. So now, what this proves? What does this prove? It just proves this statement here that if you don't know the discrete log between G and H, Peterson commitments are as binding as solving the discrete logarithm between the two. There's no difference between them. If you can solve the discrete log, you can break binding, and if you can break binding, then you can solve the discrete log. Okay, so they're exactly the same computational dependency. Okay, so this is what I wanted to say about Peterson commitments. I'll just write it down finally. Start at the bottom line. So hiding is perfect, and binding is equivalent to the discrete log problem, DLP, discrete log problem. And specifically, it's the DL between G and H. So G and H. So there's a little piece of fine print here, which is that if you want to use the Peterson commitment in practice, you have to be sure that the person that you're playing the game with doesn't know the discrete log between G and H. Okay? So this is an assumption that we make that we call a setup. So a setup is you're going to choose some parameters, but if they're not chosen in the right way, there might be backdoors. And so someone knowing the discrete log between G and H is kind of like a backdoor. It allows them to open the commitment up to any value that they want. Okay? So G and H alpha, which is the discrete log, we consider it a backdoor. So what we have is we have a setup which makes sure that there is no backdoors. And specifically in this case, what that means is that no one knows DL between G and H. Okay. Later, we're going to see other kinds of setups that are a little bit more elaborate, where you trust a little bit more. Okay, this one's a pretty simple one. How do we do that then? No one can know between G and H. If I just give you a G and H, you can't look at the two and know whether I know the discrete log between them or not. Okay, so the only way I can really convince you is to convince you that I chose them at random. Okay, so maybe I looked at stock market prices and then I, computed a number, and then I say, okay, this is the G I'm using, and this is the H that I'm using, and there's no way I would have been able to predict that. Or we literally roll dice, and I videotape it, and so you can see me rolling dice, and this is the G and H that come out. Okay, so G and H need to be generated randomly. The other thing that we haven't talked about is hash functions. An alternative you could do is you could just set H to be the hash of G. And the hash is kind of like a randomization factor, okay? And so if you see that, you're like, yeah, there's no way that they're going to know the connection between the two. There is a little bit of red tape here, which is the hash will come out as a 256-bit number. You need something in GQ. H has to be in GQ. So you got to map the hash into an element of GQ. If you're using a safe prime, that's really easy. You just square it, because the square of everything is in GQ. If you're not using a safe prime, then you have to do something that's called hashing to a curve. So an elliptic curve cryptography, you have to hash it to the curve. There's algorithms for them. They're kind of complicated, way more complicated than just doing this. But anyways, again, this is something that just one person has to do once. Okay, so NIST does it once. They tell everyone what G and H is. They tell them what's the process that they use for generating G and H. Everyone looks at it and decides, oh yeah, that looks reasonable. I don't think NIST knows the discrete log between the two. Plus, I'm not playing rock, paper, scissors with NIST anyway. I'm playing it with someone else. And so, yeah, so this setup happens once, and then that's fine. So it's not a big deal in practice, but it is, and it's one of these assumptions that we have to pay attention to. Okay, yeah. Yeah, so mod Q would give you something in ZQ. But what we want is something in GQ, right? So if I take a number and mod it, I get ZQ, which is the numbers between 0 and Q. That's great for an exponent, but not for a base. Okay, any questions about this commitment stuff? Okay, all right, good. So let's take a break, 10 minutes, and then we're going to stop talking about cryptography for a while and talk about something different. Okay. So we're done with commitments. We're going to move on to another topic. It's in math called polynomials. But one thing I'm cognizant of is we've done a lot of theory and not a lot of application. And so I just want to take a brief, kind of time out for a second and go back to use cases and just, in particular, what I want to do is I want to talk a little bit about the project. So I said that you can do your project on one of three things, or there was more than three, but there was ZK email, ZK TLS, and ZK PDF. And I just want to explain what these things are a little bit so that you can get started sooner on your project. Okay, so these two things work almost the exact same way. I think I sort of described it also in the very first class, but emails and PDF documents can be signed. Okay, what does sign mean? This is a digital signature. Okay, so what it means is that I have, say, a message. And there's an algorithm called a digital signature. and somebody signs it, and they sign it with a key that only they know. Okay, so it's a secret key. And what you'll do is you'll send that along with a copy of the message. And the secret key belongs to someone who created either the email or created the PDF. And there's some like little details here that will be part of your research to figure out exactly what it is. But so it could belong to the PDF creator. And who created the PDF? Well, it might be, say, the government. So maybe you get like a PDF that's like your tax bill or something like that, and it's signed, say, by a government. So it could be some sort of authority. Could be a company. Concordia sends you something, it's signed by Concordia. So you have this document, and you can prove that Concordia sent it to you. And there's some content in the document itself. And again, you can prove that Concordia has sent you that information, okay? Emails are the same. For emails, the only difference is that it's the server that sends it. So the mail server signs it. So for example, let's say you get an email from some address at concordia.ca. That email will come with a signature that Concordia applied to it, and I could prove to you that it came from a Concordia address, okay? And if that signature also signs the actual address it came from, then I could prove to you that, oh, j.clark at Concordia sent this to you, okay? All right, so if you want to show people a PDF or an email, you can not just show it to them, but you could prove that it was signed in a particular way. Okay. Sometimes this happens in the news, like there's a leak of someone's emails or documents, and you're like, did they actually sign it or did they actually make it up? Well, this is a protocol where you can actually prove that it was signed. Okay. TLS works almost the same way. Okay. So if you visit a website and it's over HTTPS, okay, it's as if the web server signs it. Okay, so it's similar to the web server signing it. Okay, but there's a slight hiccup with it, which is the cryptography you don't directly sign. So the web server doesn't sign it. What it does instead is it signs something that it uses to derive another key, and then it kind of signs it. It's called a MAC with the other key, okay? And so if I just write down everything that I see when I go to this URL and I show it to you, it actually doesn't really prove that it was signed by the person it came from, okay? So there are solutions to this if I want to prove to you what I'm seeing on a website, but I have to involve a third party, and these are sometimes called notaries. If you listen to those episodes, it will kind of go through why and how and things like that. But I'm just sort of alerting you to the fact that there's a notary involved. Now, for your project, you can assume that there's a notary, everyone trusts them. And so whatever you see over HTTPS could get proven. Anything that comes through a PDF, you could assume that the person signs it, or everything that comes from a mail server, you could assume that someone signs it. Okay, so what this means is that Alice is sitting here, and she has like all the websites that she could log into, and now she has a kind of a signature. I'll draw it kind of like a ribbon on that data, and every PDF you've ever received, and every email you've ever received, you can kind of prove what the contents are. Okay, now let's say there's a scenario where Alice wants to show something to Bob. Okay, she wants to show this document to Bob because it proves something about her. Okay, what it proves, that's for you to think of. Okay, so you can, if you're doing the use case, you can try and think of what are things that I could prove to someone else just based on an email that I received, or a PDF that I received, or a website that I can log into and look at. Okay? Now, the final thing is that let's say this is my credit card statement. So I want to prove to you that I made a certain purchase. I'm expensing it to Concordia, and I want to prove that I did that. And so I download my credit card statement. It's signed by the bank. I can give that to Concordia, and Concordia knows I'm not making it up because it's signed by the bank. Okay? But there's a problem, which is I don't mind Concordia seeing that one purchase, but I don't want to see all the purchases. And I don't want them to know my address, and I don't want them to know, maybe my credit card number is on it somewhere or things like that. Okay? So if I want to disclose less than the whole entire thing, that's where I can use zero knowledge proofs. Okay? So what I can do is I can feed this into a zero knowledge proof. I'll call it pi, so this is the proof itself. And it's just going to prove whatever I want it to prove. So it's going to prove that I made a purchase on this date, and it was this amount of money, and this was the merchant, because that's somewhere in this document, and that's all they learn. Okay, they don't see the document; they just see the proof of what's in the document itself. Okay, so now we have the technology to do this. So you can basically take any email, PDF, or website, and you can prove whatever you want, if it's true, about the document, and not show anyone the document itself. All right? And because you can do this, people are envisioning, and it's very efficient. It's not necessarily efficient to generate the proof, but for Bob, he gets something and he can verify it instantly. So Bob could be a web server, a phone app, or anything like that. So Bob can be, implemented as very efficiently. So now what you can do is you can walk around proving things about who you are, things you did in the past, things that you bought, as long as you can tie it back to some source that was signed, which you can do if you got it through email, PDF, or TLS, or you can assume that you can do that. Okay? And so the use case for the project would be like try and think of use cases where this is interesting. Okay? And if you listen to the episodes of the podcast, they have lots of ideas as well. And you're free to use one of the ideas that they come up with. And the episodes are just to get you started. That's not like the ground truth. You can also Google or ask ChatGPT or whatever on ZK-TLS and what are the use cases and things like that. But start thinking about it, and I want you to sort of get the right mental model of what's happening. So you have some signed data, and I'm proving facts about the signed data. And it doesn't have to be one document. It might be like I have 100 documents. And maybe Bob, it's not a privacy thing. You could send the 100 documents to Bob. You don't care. There's nothing private in it. It's just that Bob doesn't want to receive 100 documents from you because that's going to be 100 megabytes. And he would rather just get something that's really quick. Okay? So that's, it doesn't necessarily, I sort of pitch it as a privacy thing, but basically what you can do is you can prove that things backtrace to things that were signed, and it's very efficient for the person to verify that proof. Okay, questions about that? Yeah.
Do we use like a similar thing for all of it, like email, websites?
Yep.
PDFs?
Yep, so the hard part is the ZKP here. So like how do you write that proof out? And that's what this course is about. So I'm building up to showing you how to write this proof out. But this, you can do it for any computation. So you can prove any fact about anything. As long as you can use a circuit to specify exactly what you want, then you can do it.
It will be like a case study, like how I'm going to implement the zero knowledge proof.
Yeah, so for the use case one, I want you to think more about the inputs and the outputs to the ZKP, less about the ZKP itself. Yeah, I want you to understand it so you know that, like, for example, you might need a notary, or like you should be able to know why. But the thing that I'm building in this course is so general that once you have it in your hands, you don't have to know about zero knowledge anymore. You just the same way you can program and you don't have to know about compilers and operating systems and stuff like that. It's the same idea. Like there's this ZK technology and you just tell it what you want to do and it will spit out the proof that you need. And so for the use case one, you can concentrate more on the actual use case itself. And you can almost not talk about zero knowledge at all. But yeah. So that doesn't have to be a deep dive into how it's working under the covers. Yeah. If you like to understand how it's working under the covers, that's a different kind of project that you can do as well. And yeah. Okay, other questions about that?
So,
Yeah.
one more question. Do we like create a project where I send an email, like, should be a working project or?
Not necessarily, but you might, so there's different ideas, there's different ways to like kind of make your project more substantial, right? So I have this idea, I can go into a lot of detail about the idea itself. That's one way to make it substantial. I can try and get it working like a prototype and try and use some of the toolkits, so that would be a different way. Or I can try and explain like what's happening under the hood, like in terms of the zero knowledge. So there's no right or wrong way. It's just you have to substantiate the project somehow. But that would be one way, but it's not necessary. Yeah. Okay. Yeah.
This project, how to design a system?
Yeah, so the first thing that you start with is just a use case. So like, I know like the government sends this kind of email and it'd be really nice if I could show that to someone else, like whatever the scenario is. So that's actually the first contribution, and it's probably the hardest, right? It's more of a creative thing where you have to think of how you could use it. And then once you have that, then you can talk about the details. And again, you can drill down on like the details of how you would do it in real life, or whether you can do it in real life, or this would have to change to do it. They can be hypothetical too. It doesn't have to be like, I'm getting these emails today, but you could say all the government needs to do is like sign these emails, and then now all of a sudden you can do this whole thing. But the answer is it's like more of a creative type of thing, that first step. And then once you have that idea, then you can choose how you want to like kind of substantiate the report with details. Does that make sense? Yeah, okay. Other questions? Okay. All right, then moving on. Okay, so we're going to switch gears for a bit, 1 or 2 lectures, and we're going to talk about something called polynomials. And essentially, we now know about commitments. And to know about commitments, like a Peterson commitment, we needed some like number theory. So we spent a lot of time on this stuff. Now I'm going to talk to you about polynomials. And when I'm done, what we're going to do is we're going to put the two together. Okay, so we're going to come up with commitments for polynomials. Okay, so it's going to look like a Peterson commitment, but because I'm committing specifically to a polynomial, it's going to have some extra features. Okay, so commitment for a polynomial. And then what I'm going to do is I'm going to use this to build a SNARK, basically a zero knowledge proof for a circuit. So I have a circuit. I'm the prover, so I know everything about the circuit. I know all the inputs and outputs, but I'm just going to prove to you what the output is without showing you the whole execution of the circuit. Okay, so this is kind of the roadmap of where we're going to go. And we're also going to kind of go directly from polynomials to here as well. So this will have 2 ingredients. So one is a polynomial commitment scheme, and then the other is called the poly-IOP, Polynomial Interactive Oracle Proofs. And it sounds complicated, but we'll explain that later. Later, when you're at the end of the course looking back, you'll know what these 2 terms are and how they combine. But for now, you don't know what these 2 things are. Sorry?
You just spelled it out.
Yeah. So, like, you mean like right out what they are? Yeah. So we're going to have a polynomial commitment scheme. And we're going to have a polynomial interactive oracle proof. I'll write it down here. But anyway, so we're today and next class will just be in this box. We won't worry about this stuff for later. Okay, what's a polynomial? What does it have to do with? Just tell me anything you know about a polynomial. Say it louder. Okay, so there's an unknown, so there's going to be a variable, correct? Anything else?
We have like an equation.
Okay, so there's an equation. The equation has some unknowns. Okay, that's good. What is the equation doing? Let me take a different approach. Is a polynomial something you can kind of see and visualize?
On a graph, we
Okay, so it's sort of a curve or something like that. Okay, so a polynomial is going to it's something you can visualize. Okay, so we might have x and y coordinates, and then a polynomial is going to be like some sort of curve. So I'll write p of x. All right. Can the curve look like this?
No, there's
Okay, so at this
same as
value of x, we have more than one y value. Okay, so one of the restrictions on a polynomial is that there's only one y value for every x value. This is 2 dimensions, so we have a y and an x. Could we have a 3-dimensional or 4-dimensional or 5th-dimensional? We can, okay? Good news for you, we will only do 2-dimensional, okay? So we call these univariate polynomials. It's the simplest kind of polynomial, okay? All right, can any curve with this restriction in place, can any curve that I draw be a polynomial? Okay, so we think yes. So the answer is actually no. So there is a bunch of things that I could draw that are not polynomials, okay? Like I'll give you a simple one. I could draw something like this, straight line, and then it shoots up like this for a straight line. So there's not going to be a polynomial for that, okay?
So are
Yeah.
we restricting ourselves to the univariate, and there's actually something with the multivariate as well?
That's also true with multivariate and univariate, that there are things that you could draw that there are no.
What I wanted to
Yeah.
refer to before, are there applications of multivariate polynomials in CKPs?
Yes, there are. Yeah. So there are ways that are actually more efficient, arguably, of using multivariate than univariate. Yeah. So univariate is a simplifying assumption, and I'm showing you like the simplest possible one. Yeah. Okay. Yeah. So you'll see a lot, and if for a project, if you wanted, you could say, what if I took Planck, which I'm teaching you, and moved it to multivariate? So they call it a hypercube. Then what can you do? And so there's some papers, and some of the things I mentioned as possible projects are about that. So there's a couple that use multivariate instead. But yeah. Okay. All right. So some functions we can describe with polynomials. Some we cannot describe. Okay. What gives? Like why can I describe some and why can't I describe others? It's that polynomials have a specific mathematical formula. Okay, so anything I can describe with that math formula, I can capture, and then there might be some other stuff that just it doesn't fit in that formula, and so it's not going to fit. Okay, so what is that formula? Can anyone tell me what it looks like? So it's something you probably know, but maybe don't know the name of, but you know the format of a polynomial as a specific format. Okay, so no sign. Sorry? Yeah, okay, so ax plus b is good. Is ax plus b a polynomial? What is ax plus b? What do you know it better as? Okay, so it's a straight line. Okay. Straight lines are polynomials. Okay, so a straight line is a polynomial. It's the second simplest polynomial. There's one that's simpler. What are some other things that are polynomials? No. Or speed? Do you say speed? Okay. But that's like derivatives in calculus. Yeah. Okay, does anyone know, like, what if you go from a line, what's the next most complicated object? It's, yeah, okay, all right, so it would look something like this. Okay, so as we get more complicated, so this is called a parabola, and then we can keep adding terms. So what's the pattern? The pattern here is that I'll write it backwards, but you have some number, we call it a coefficient. So this is just an integer. And then you add to it another coefficient times x. Then you add another coefficient times x squared, and so on. And at a certain point, you'll stop. Okay? The more of these terms that you add, so I'll call this a term, the more complicated your curve can get. Okay? So the simplest thing that's a polynomial would be that I just have C0 and then I stop. Okay? So P of x equals C0. What does that look like visually? It's a constant function or a straight line. So it's an unsloped line. So for example, you can just think about, let's say P of x equals 5, right? Well, what's P of 1? It's 5. What's P of 2? It's 5. What's P of 3? Like doesn't change with x. So you're just going to get a straight line all the way across. So we call it a constant or an unsloped line. Let's say that we have P of x equals C0 plus C1x. What's this? So C0 and C1, we can call them A and B, right? So that's just A plus BX, right? What's A plus BX? We just had it. So it's a line with a slope. And then Px equals C0 plus C1x plus C2x squared is going to be a parabola. And then you can keep going. So you get more and more complicated things. Okay? So it's basically, it's a set of lines that can be drawn. They always have this format. Okay? Why do we care about lines that have this format? So there's two reasons why. The first one is that they actually show up a lot in real life. Okay, so there's a lot of straight lines and there's a lot of you throw a ball and it follows a certain pattern and things like that. Okay, so there's a lot of things in real life that will fit one of these formulas. So we like it for that reason. The second reason we like it is what we can do is we can convert a set of points into a line, into a polynomial in a way that's very efficient. So let's say I'm out in the real world and I'm measuring something and I see that for every x, this could be speed or something like that. So for different, x could be time and y could be speed or something like that. But anyways, I take a bunch of measurements. Okay. Then what I can do is I can fit a line through those. Okay. And an easy way to fit a line is to make it a polynomial. Okay, so I can fit a polynomial through that line. All right. And I will now have a math equation that describes all of those points. Is that math equation exactly the same as the line I'm observing? Not necessarily. It's an approximation. Okay. It's a polynomial approximation of it. Okay. But what I did is I can, there's a formula, we're going to look at it. It's called interpolation. And interpolation says you have a bunch of points, you can draw a polynomial through those points. Okay, we're going to use that. Okay, so eventually we're going to have a circuit, and the circuit is going to have a bunch of values, and we're going to draw a line through those values so that our whole circuit is now a line. And then I'm going to like prove to you that the circuit is right because it's a line. It sounds crazy, but that's eventually what will happen. Okay, so we like polynomials. They're useful because they model aspects of the real world. And the second is interpolation, which is I can convert a set of points into a line that runs through those points. Okay, when I look at this equation, what is C? It sort of says, but what does C represent? Let's think about a straight line. So let's actually look here. Okay, so I have P of x equals C0 plus C1x. What are C1 and C0? So they're not the variable. So the variable is x. Yeah? So x is, and where is x on this chart? It's the horizontal line. Okay? I have a y here. Where is y in this equation? I don't see a y. Okay, so it's the output of the polynomial, so I can write y. Okay, so y is the p of x. And sometimes when we chart it, we'll just say x and p of x as opposed to y. Okay? Okay, so these integers are going to specify what the line looks like. Okay, so for a straight line, it might be like, where does it intercept the y-axis, and what's its slope? Okay, for a parabola, it will have a different, there'll be some interpretation. You don't have to know what the interpretation is. Okay, x is the variable, and so what I do is I can draw the whole line just with the c values. Okay, so I don't need the x values to draw the line. So the line itself is specified by the c values, and then what the x value does is it just says pick a point like this, and then you can figure out what the y is that corresponds to it. Okay, so the x here, it's not like a number that's locked in. So when I tell you my polynomial, I'll tell you what the coefficients are. I'll say it's 5 and 17 and 3, but I don't tell you what x is, because otherwise it's just a number. When you multiply this out, it's not a polynomial, okay? So the x here is the variable. So you're allowed to choose different x's. It has different values for different x's itself, okay? So I'm going to use a notation to try and make this a little easier, because sometimes when you write this down, you forget, oh, the x is a variable and the c is not a variable. Sometimes what will happen is people will use capital X. And so you're supposed to know that if it's a capital letter, it's a variable, and if it's a small number, it's not. But to make it even clearer, what I'll do is I'm going to, instead of writing x, I'm going to write like an empty box. Okay? So think of this as like a box to put a variable in, a slot. It's like an empty slot. Okay? So you can put whatever number you want in there, and then I'll write things like C0, well, right, like C0 plus C1 times the box, plus C2 times the box squared, plus C3 times the box cubed, et cetera, et cetera. And so if you're like, I want to know what this is evaluated at 4, then you just put a 4 in the box. And the C values will be numbers, and then you evaluate it, and then you're done. Okay? But if you want to change from 4 to 5, you can change from 4 to 5. All right, so that's the notation I'll use, and it will be a little clearer hopefully later. It will pay off. Okay, here's a couple other just kind of terminology things. So terms, I'm writing them from the smallest to the biggest by powers here. So this is like the largest term, because it's the one that has the biggest exponent on it. And this we call the degree of the polynomial. Okay. So when I write it out, if it stops at x squared, then it's degree 2. If it stops at just x, then it's degree 1. And by the way, you can also think of this, if it bothers you that there's no x on the first one, you can think of this to the power of 0. Okay, so the last term that we'll write down, we'll call it d, and d is the degree. All right. How many coefficients, if degree d, the polynomial is degree d, how many coefficients are there? D plus 1, okay? So sometimes you'll see d plus 1s and you'll be like, what's the plus 1? And so it's just remember that there's an extra. Okay, I want to draw a straight line. How many points along that line would I have to know to be able to write that line down? 2. Okay, if I know 1, do I define the line? I can't. There's a lot of lines that would go through that same 1 point. Once I have 2 points, then I can fix the line. If I know 3 or 4, that's fine. It's helping me, but I don't need it. Okay. The smallest number of points to describe that line is 2. Okay. All right. So for a straight line, I need 2 points. What's the degree of a straight line? 1. Okay, why? Because C0 to C1 to the 1, x to the 1. Okay. So a straight line has 2 points, and it has 1 degree. That pattern will follow. So if you want to talk about parabola is going to be degree 2, and you're going to need 3 points in order to specify it. Okay. If you just have 2, there's a lot of parabolas that fall through 2 points, but if you have 3, okay? So in general, we're also going to need d plus 1 points to lock down a degree d polynomial. Or if you want to think about it the opposite way around, you could say, I'm going to write down a certain number of points. So let's say I have 50 points. I want to find a line through it. The degree of that line is going to be 49. It's going to be 1 less than the number of points that I have, okay? But I'm going to have the same number of coefficients, okay? All right. All right, then the final thing is I'm going to restrict the polynomials that we talk about. In 3 ways that you'll be very thankful for, because they all make your life easier. The first thing is that I'm only going to have integers. Okay? So everything, every coefficient, every x value, everything is going to be an integer. There's not going to be real number, or sorry, there's not going to be real numbers in the sense of decimals or complex numbers or anything crazy. Okay? So we're just going to do integers. Second, I'm not going to let the polynomial get bigger than q. How am I going to keep it within q? I'm going to mod it by q. Okay? So we're going to do, they're going to be integers. Everything will be mod q. All right. And this q will go back to the q that we talked about in cryptography, but you don't have to make that connection yet. To write down a polynomial, what kind of operations do I need? Do I need exponentiation? I do, right? Because I have x squareds and x to the d's. Do I need multiplication? I do. Do I need addition? I do as well, okay? So we call this FQ. And FQ just means the integers from 0 to q minus 1. And you have support for addition, and you have support for multiplication, okay? FQ is very close to GQ. GQ, we only had support for multiplication. We couldn't do addition, but with FQ, we can do addition and multiplication. Okay, this is a detail that just forget about for now, but I'll just write it here so it's in the notes. Okay, the third thing is it's going to be univariate. So what that means is it's going to be p of x, not p of x, y, z. Okay, so you can have polynomials where it's like, you know, c0 to the x times y, and then x squared y, and y cubed x, and things like that. So those are multivariate polynomials. So we're just going to consider one variable itself. Okay, so these are kind of arguably the simplest polynomials that you could use. All right. All right, so let's say that Alice has a polynomial she's thinking about. She's like, okay, I'm thinking about this polynomial. I want to tell Bob all about my polynomial. What does she have to tell Bob so that Bob can also think about the same polynomial? Okay, so what she can do is she can tell the coefficients, okay, in the right order. Do you have to send the x's? No, because they're variables anyway. And do you have to send that it's 1, 2, 3, the powers? Well, it always has that same format. So as long as I get the coefficients and I know they're in the right order, that's all I need, okay? So what I can do is I can send C0, C1, C2, CD. Okay, and how many things am I sending? So D plus 1. And each of these, because I'm doing everything mod Q, these are each they're all going to be from ZQ. Okay, so I'm sending D plus 1 ZQ things over to Bob. Now Bob is thinking of the same polynomial that I'm thinking of. Is there anything else I could send instead? What if I send points? If I send Bob a bunch of points, he can draw the line through it and come to the same polynomial. We agree? Okay, it will be more work for Bob because Bob's going to have to run this interpolation algorithm. Okay, but we could get Bob to compute the same polynomial by sending him a bunch of points. How many points would we have to send? D plus 1. Yeah, so it's the same, basically the same thing. So I could send, here's x0, y0. And since I introduced this notation up here, let me actually use that notation. Actually, it's just easier to write it like this. I'll write the p of x0. That's like the y. I'll do it as y. They're all equivalent notations. But so I send x0, x1, y1, x2, y2, x3, y3, etc. And again, I'm going to have d plus 1 of these points. Okay. Then what Bob can do is he can also reconstruct the same polynomial. Okay. What are the x values that I'm using here? So I'm using x0, x1, x2, x3. What x value should I use? So let's say I have this line. I have to send 10 points for Bob to understand what this line is? What 10 points do I send? Okay, so I can send any 10 points, okay? As long as they're different, yes, exactly, yeah. So I can send any 10 independent points, okay? So a simple thing I might do is just send the first 10 points. So I might send, these 4, okay? But if I sent this point and this point and this point and this point, he'll still reconstruct it when he draws a line through it, okay? So the x values that he sends, we call the domain. This is called a domain. We denote it h, so not a hash function. And it can be any domain is okay as long as x's are independent. I'll just say they don't repeat. Okay, and importantly, Alice and Bob could know what the domain is ahead of time. So NIST could say, oh, you should always use this domain. Always use 0, 1, 2, 3, 4, 5. So then what does Alice have to tell Bob? Well, Bob already knows the domain, then she actually just has to send the y values themselves, okay? Every y value is from ZQ. There's d plus 1 of them. So telling you d plus 1 coefficients or telling you d plus 1 y values is exactly the same. It's the same amount of information. Okay. There's a third thing that you could send that's actually a special case of this, but I'm going to split it out because it's something that we're going to see. Otherwise, I wouldn't bother talking about it. What you can do is you can send a set of roots of the polynomial. I'm going to write 0, R1, R2. Okay, what's a root? In this case, it's going to be d minus 1. I think. It doesn't even matter. But no, d. I'm going with d. Okay, what's a root of a polynomial? So a root of a polynomial is when it crosses the 0 line. So in the other one, I drew it and it never crossed. So this is a root. This is a root. This is a root. Okay, and so you can actually think of it as a set of points, but it's a set of points where the y value is 0. Okay, so you'll have an x, and then it will be 0. And then you'll have x1, 0, x2, 0, etc. Okay. Is it any better than sending an arbitrary set of points? So the reason that we like roots is the way to turn a set of roots into the polynomial is easier than the way to turn a set of arbitrary points into a polynomial. Okay, so the algorithm I can write in a single line, and it's really, really easy. In fact, it's so easy I'm just going to write it beside it. So here, what Bob will have to do is he'll have to do this interpolation. Interpolation is kind of weird to explain, but the roots of polynomial, if you know the roots, then all you do is you do x minus the root times x minus the next root times x minus the next root, etc. You multiply that whole thing out, you're going to end up with a polynomial, and that polynomial will be the right polynomial that goes through these roots. Okay, so it has a nice like kind of closed form equation for computing. So that's why we sometimes will talk about roots themselves. Okay, 2 other facts about roots. I have a straight line. I'm going to draw it. How many roots does a straight line have? Okay, so if it's a unsloped line, it's going to not have any roots, unless if it happens to be the line at 0, and that's usually considered a special case, a corner case. So a polynomial that's just y equals 0 is called a zero polynomial, and that's like, it has different rules that apply to that. We'll use zero polynomials a lot, but anyways, if so it's unsloped, it has no roots other than the zero polynomial. What if it's a sloped straight line? What does it depend on?
The shape itself, it could be like a parabola above it.
Okay, it's a straight line. It's straight and it's sloped. Okay. Let me put it, okay, is it possible that it doesn't have a root? For a straight line that's sloped. It will eventually cross the y-axis somewhere, okay? Now, when we say we're going to restrict our integers to q, we might think about whether that's true or not for us, right? But anyways, back in the infinite case where we have an infinitely long thing, it will cross the y-axis at least once. Could it cross it twice? No, because otherwise it would have to turn or curve or something. It's no longer a straight line, okay? Sorry? Yeah, so in an infinite world, yeah, you can have positive, negative integers.
No, for this, you said integers, right? So we don't consider negative integers.
Sorry, I'm not catching what you're saying.
Ever we mentioned for this course, we are only sticking to integers.
Oh, yeah, sorry, I understand now. For bivariate, it also will, so a root is a little more complicated because you have more than one axis. So you have to define which axis is it crossing. But it will cross the plane, the zero, like say, imagine like a z-axis that's coming out of here, and we call this the plane. The line will cross the plane exactly once. Yeah. Just forget about multivariate. Yeah. Okay, so a straight line will have one root. And what's the degree? Degree is 1, right? What about a parabola? So a parabola is something that looks like this. Okay, it's going to cross exactly twice. Okay, so the number of roots and the degree are the same. Okay, so the number of roots. That's why I wanted to write a d minus 1. So it is actually right. The number of roots and the degree of the polynomial will be the same. Okay.
Like for the parabola, where did I split that? Not where the
Yeah, so the
above the line, or in the case where it just touches the line after it affects the point.
Yeah.
That would be 1, right?
That's correct. Yeah, so you could have a parabola that's like this, and then the answer to that is because we're doing things that are infinite, there are complex roots. Okay, and so there are roots to this, but there are no roots in what you're actually looking at now. You have to kind of look in another dimension. What that means here is because we're working in this field, you might not have, so a better way of putting it is that if I give you a set of d roots, you could, and you do this expansion, you'll get a degree d polynomial. So going from roots to polynomial will work. If I want to go backwards, if I have a degree d polynomial and I want to find the roots, I can't always do it. Okay, so that's called factoring. And the reason I can't do it is because I might have something like this. Yeah, so I might have all the roots are here, but they do exist somewhere. They're just in another dimension. Okay, so it could be a complex root, or here, what the other dimension is called a extension field. And so the roots will be in this extension field rather than in the field limit itself. Okay, but when we use the roots, we'll never go from polynomial back to roots. We'll always go in the other direction only. Yeah, and that's actually something that I want to talk about next. Which is how do you move between the two things? So I could have a set of points. I could have a set of coefficients. And I could have a set of roots. Okay? All of them could describe the same polynomial. Okay? And if I have it in one form, can I turn it into the other form? Okay? So let's say that Alice sends me the coefficients, but I actually really want a set of points. Okay? Or what actually happens a lot more is Alice sends me a bunch of points, but I need it in coefficient form for whatever reason. Okay? Then can I convert easily between these two, and how easy is that? Okay? So this is how it works. Can I turn points into coefficients? I can. I need an algorithm called interpolation. Sorry? So that was for roots, right? You're talking about this, right? Okay. So I have a set of roots and I want to turn it into coefficients. I can just do multiplication, yeah? So it's easier than, well, we don't know what interpolation looks like, but I can promise you it's more complicated than just multiplication. It's not that complicated, but it's more complicated than just multiplication. Okay. Let's say I want to go backwards, right? So I have all the coefficients, and now I want to find 10 points. How do I do that? Okay, I can just plug it in. So I know the coefficients, so I can write out the polynomial equation, and then if I want to see what the y value is for x equals 1, I plug a 1 into the boxes, and then I compute the y. Okay, so we call that evaluation. All right. Let's say I have coefficients and I want to turn it into roots. This is where I might get into trouble. Okay, so we call it factorization. And I'll note that it might not be possible. Okay, so some polynomials can't be factorized, at least without like doing it in a different dimension. Okay, but for this course, we will do this, and we'll do this, and we'll do this. Okay. Now, what about between roots and points? There's no, basically, I don't know of any way of directly going through it. Usually what you would do is if I want to turn roots into points, I would go to coefficients first, and then I would go to points. And similarly, if I had points and I wanted roots, I would turn it first into coefficients. I don't know of any algorithms that goes directly between the two, okay? So usually we can reach between the two by going through coefficients as an intermediary representation. Okay, last thing I want you to think about is how complicated are these operations, okay? So let's start with the evaluation. I think that one's the easiest. So for evaluation, what I'm going to do is I'm going to pick an x value. I'm going to compute this equation. I'll get the y value. So now I have 1 point. Then I'm going to do it again. That will give me 2 points. And then I'll do again. That will give me 3 points, etc. Okay? How many multiplications would I have to do to do that? So I'm going to compute d plus 1 points. So I'm doing d multiplication, I'm doing d evaluations of the polynomial equation. Okay? But how many multiplications do I have to do to evaluate one polynomial? So then tell me in terms of the degree. So I have to do d of them, right? Because it's d long. Yeah? So to get 1 point, I do d multiplications. To get 2 points, I get d multiplications. And I keep going until I have d points, or d plus 1 points. So how many multiplications did I do in total? I did d times. Okay, so d times d is d squared. Okay, so this operation is going to be OD squared. So that just means it's whatever the degree. If it's a degree 1,000 polynomial, you're going to do about 1,000 squared work. Sorry? So this is for the, so to, you have the coefficients, I know them, and I want d plus 1 points.
Did we decide OD square for that?
Yeah, so that's what we just did, right? So just to clarify, so I have the coefficients, so I have this equation written out. I want points, right? So what I do is I have to figure out x, y pairs. So I start with 1x, I plug it in, and I get the y. Then I do it again and again and again until I get all the points. Did it make sense? Okay, so every time I plug, like here I am plugging the number 4 in, and so I get whatever it is. Okay, so this is order OD squared. Interpolation, going back the other way, I'll tell you it's also the same. Okay, I'll show it to you, not this class, but I'll show it to you next class. What about multiplying out the roots? So I have d of these terms, so it's x minus r, x minus r1, x minus r2, up to d. Okay, so how many multiplications is that? So it looks like it's d, right? But the problem is that every time I make one of these terms, like let's start solving it, I have to do x, like say I just multiply these two terms, I get x squared plus 2x minus r0 minus r1.
Could you compute x's first?
So then I would have points. Yeah, so I could do that if I want to go, to the coefficients somehow through the points maybe, but if I just want to go directly from roots to here, yeah. So now I have 3 of these terms, then I multiply the x in, and then I have 4 terms. And so every time I expand one term, I have to do it across the whole equation. So this ends up being d squared as well. This is expensive. So it's going to be way more than OD squared. Not way more, it might be like cube, I think it's cubic, but then also it might not be possible, and we're never going to do it anyway, so I'm just not going to write a number. But don't think of it as it's more than these 3 things. Okay? All right, last thing, there's a trick. Okay? One thing about interpolation and evaluation is, let's start with evaluation. So I'm turning coefficients into a set of points. I said you can use any x values you want, right? So if I just want to write d plus 1 points down, it doesn't have to be the first 10 points. It could be a point here and a point here and a point here, okay? And similarly, if I give you a set of points and you're going to draw a line through it, I can give you any set of points as long as there's d plus 1 of them. Okay, so is it possible that there's a nice set of points that I could give you that would make these 2 things easier? Okay, so if I just give you like points at random, you're going to be stuck at d squared. Okay, but if I give you a nice set of points that has some structure to it, maybe there's a way I could do it a little bit faster. Okay, so it turns out that that exists. There is a nice set of points I can give you. They're called roots of unity. Sounds crazy, but it's not so crazy. It's actually something you've already seen. And if I give you the domain in this nice way, we can lower the complexity of this to O d log d. And we can do the same for evaluation. Okay, so interpolation, we call it a fast Fourier transform. Might be something you've seen before if you've done electrical engineering. And then this is the inverse fast Fourier transform, IFFT. Okay, what does that mean, d log d? Is that big? First, is d log d actually smaller than d squared? Sure about that?
Yes.
Yeah, okay. How much smaller? Like a little bit, a lot? A lot? Okay, I agree with that. So let's just sort of think about kind of a number line. So let's say that we have something that runs in constant time. We call that O1. We have something that runs in linear time. We'll call that OD. And then we have something that's running in quadratic time, which is where we were. Okay? So what I'm saying is that d log d is less than d squared. So it's somewhere along this line. Okay? Is it going to be bigger than OD? Is it going to be on this side of the line, or is it going to be on this side of the line? Okay, it's going to be on this side because there's a d term here. So I'm taking something that's already OD, and I'm multiplying it by something. So the only way this could get smaller is if the log was less than 1. Otherwise, it's going to get bigger. And logarithms are defined that they'll always be bigger than 1. Okay. So we're over here somewhere. Okay. So let's say I pick a halfway point. What's this halfway point? Very, very close. You right idea, but 2 over 2 is 1. Oh, O of d over 2. So it's not that. That would actually be here somewhere. Okay, so d to the power of. No, I think you're right. Just say it. I just didn't hear. So that's the same as here, right? Yeah, but 2 over 2. That's what I thought you said originally. That's 1. D to the 1. You want a d in the exponent? You're so close. You're so close. Okay, what's the power here? Okay, so this is the same as d to the 1. This is also the same as d to the what power? Okay, yeah, so 1 by 2 would be halfway. What's another, a nicer or more common way of describing d to the power of 1/2? Square root, okay? So sometimes in complexity you see square roots, okay? So this would be, it's actually d times the root d. It would be 3 over 2 because, but here, the halfway between here is root d. Okay, so this is something you see commonly, okay? So you're kind of like, it's order d, but I reduced it to root d. So you can think of root d as kind of like the halfway point, okay? So you're sort of saving half of it. It's half as complicated. You're halfway on the way to making it linear, okay? In general, we want things that run fast, so we want things closer here, okay? Now, where's log? Okay, do we think log is like in this region, or is it in this region? Is it bigger than root d or smaller than root d? It's okay if you don't know, but just guess. So I heard smaller, so that's right. Okay, it's smaller. How much smaller? Okay, it's a lot smaller. Log d is like so close to 1 that it might as well be 1. Okay, so this would be O log d. Okay. And then similarly, if we have d log d, we aren't quite at OD, but we're so close that we might as well be there. Okay. So generally, if I can take something that's d squared and make it d log d, I love to make it linear. I'd like to make it OD. Okay, so that would be a big improvement. But if I can get it to d log d, that's like so close to being linear that in practice we don't even really care about the log d part. Okay, So log t is just, it's a little bit extra that you have to do, but it's, you know, it's so close that we might as well not care, okay? So for SNARKs, by the way, if we think about the size of the proof, what I'm going to show you Planck, it's O1, okay? So it's constant time. But there are SNARKs that are log d, or log like the complexity of the circuit. And again, we still consider them succinct because they're so close to being constant that we don't really sweat about the fact that they're just logarithmic, okay? And we can also think about how much time does the verifier take. So if let's say the circuit is like really, really big, it's 10 million gates. For Planck, it will actually take the same amount of time as if it were 10 gates because it's constant, but there are SNARKs where it would take log d, so it would take, yeah. What's the, which? So it depends what you're doing. The prover still has to make it. So the prover is going to have to do interpolation, so it's going to have to do d log d. So that's the sort of the factor of it itself. So, and then the size of the circuit depends on what you're proving, okay? So let's say that we go back to this use case where I have some random HTTPS page and I want to prove to you that like this, my name and this number appears on that page somewhere and it's signed by someone else. We're talking about, it's usually expressed in terms of constraints which are roughly the same as the degree of the polynomial, and it would be like millions plus kind of thing, yeah? So, but not, maybe not billions. So you can think of degrees being like more than 100,000 and probably less than a billion, I would say, somewhere in that kind of range. That would be like a standard thing that you would do in real life. Yeah. Okay. All right, so these are polynomials. This is how you move between them. And next class, what I'll do is I'll show you, you won't have to do it by hand, you just have to believe that it exists. But I will show you what interpolation is. I'll show you the nice domain that you can use to make it faster. I'll show you visually why it gets faster because you use the nice domain. And the one thing though that you do need to know is that what that nice domain is. Okay, so that nice domain is something that we'll have to be aware of. We can't just ignore it when we talk about when we get actually all the way up to Planck. We're going to have to think about that nice domain. Okay, all right, that's it for today. So I'll see you next week.